We call this the electromagnetic signature. And the electromagnetic signature of different materials at terahertz frequencies is very different. So you can immediately tell what material you're sensing. And when I say materials, I do not only mean inorganic materials. I also mean organic biological structures in your body. And that's why we can use this to detect different biomarkers, but also to detect maybe how much water your skin cell has and relate that, for example, to skin cancer.
What's the first thing that comes to your mind when you hear the word connectivity? A laptop, a smartphone, maybe a smart home, even an extended reality experience. That's all true, but what would your reaction be if I told you that your own body cells can be connected to the internet in the future? The applications and usage of the internet are multifaceted and expanding daily. The Internet of Things, Internet of Everything, and Internet of Nano Things are approaches for incorporating the internet into our personal, professional, and social life, making the impact of the internet even more pervasive, personal, and intimate. I am Renuka Racha, and today in this episode of Tech 2030, a 6G World podcast, we will talk about the Internet of Nano Things, a world where new types of wireless communication devices enabled by nano and biotechnology promise to push engineering to previously unexplored application domains. The research on nanoscale communication and networks aims to develop systems for interconnecting these novel devices at the nanoscale, namely the Internet of Nano Things. This research can be broadly subdivided into two areas. 1. Electromagnetic nanocommunications, and 2. Molecular communications. Electromagnetic nanocommunications bring new challenges to the traditional wireless paradigm, as nano devices can only operate at extremely high frequencies, like in the terahertz band and above.
Terahertz communications means many things. On the one hand, you can think of terahertz communications as, for example, what's going to come in your next cell phone as part of 6G, and that's great. But actually, terahertz communications is much more than that.
That's Dr. Joseph Yornet, Associate Professor in the Department of Electrical and Computer Engineering and the Director of the Ultra Broadband Nano Networking Lab at Northeastern University.
In addition to all the macro scale applications, there are all the nanoscale applications in which we take advantage of the very small size of terahertz transceivers and antennas to create new type of devices and therefore new type of applications such as wireless nanosensor networks or even the Internet of Nano Things. Applications in which these individual devices are comparable in size, for example, to the cells in your body. So we can start talking about something very different of what we know today.
The rising dominance of IoT technology is facilitated by physical objects being linked to the internet by a wide variety of wireless technologies. These include short-range technologies, typically using unlicensed spectrum such as Wi-Fi, Bluetooth, Zigbee, and Z-Wave, and wide-area cellular technologies using licensed spectrum such as 4G and 5G. 5G mobile technology is designed to truly implement a heterogeneous network, which is just what IoT optimally requires. It is anticipated that over time, massive numbers of IoT devices will be connected to the internet via 5G and beyond, supporting ultra-reliable and low-latency communications. As this pervasive and ubiquitous interconnection of the everyday devices continues into the future, the exchange of information and access from and to the internet for their monitoring and control are even more essential.
What's the advantage of doing terahertz sensing? Well, when you go to high frequencies, your wavelength becomes smaller. And if your wavelength becomes smaller, you can see smaller things. So there is an intrinsic benefit of going up in frequency, which is that you can see smaller things. And that's great. The other thing is that when you go to higher frequencies, the energy of your signal becomes higher. And this is how some people in communications sometimes, it's easy to confuse terms. Sometimes when we think of the energy of a signal, we think of the power of the signal multiplied by time. No, I'm talking about the photon energy of the signal.
Here things starts to become a little bit tricky, but also very, very exciting. Dr. Yarnett will help us understand the concept.
At the end of the day, an electromagnetic signal, you can understand it as a wave, or you can understand it as a collection of particles, which in electromagnetics we call photons. The higher the frequency, the higher the energy that each photon has. Then, of course, the number of photons tell you how much power you have. What I'm saying is that at terahertz frequencies, even if it's with a few photons, these photons start to be energetic. And because they are energetic, they can interact with the atoms, with the molecules of the obstacles that they encounter. And the result of that is that terahertz signals can be absorbed at some frequencies by some materials. And if instead of looking at one frequency, you do a frequency sweep, what you will see is that different materials have a very different absorption response. We call this the electromagnetic signature. And the electromagnetic signature of different materials at terahertz frequencies is very different. So you can immediately tell what material you're sensing. And when I say materials, I do not only mean inorganic materials. I also mean organic biological structures in your body. And that's why we can use this to detect different biomarkers, but also to detect maybe how much water as your skin cell has and relate that, for example, to skin cancer.
Almost a decade back, Dr. Yarnett and his colleague, Dr. Ian Echelids, started thinking about the interconnection of nanoscale devices with existing communication networks and ultimately the internet, defining a new networking paradigm.
It was in 2010, so 11 years ago, that again with Professor Echelids, we published this paper on the Internet of Nano Things. In 2010, what we were saying is that we would have these machines which are as small as the cells in your body, which means that, of course, they don't need to be in your body. They can be of your body if it comes to that. They can be wearable. They can be in the clothing that you're wearing. They can be in the paint of the walls of our buildings, right? They can be anywhere. And of course, they need interfaces to communicate with the outside world and traditionally the macro world. I agree that in 2010, this may have sounded a little bit of science fiction. We're in 2021. Well, how far are we? Well, today, right, more or less, people are used to have wearable devices, right? You yourself or myself here are wearing, a smartwatch that can, of course, measure large, indicators of your body, fine, but a wearable device that can also serve as an interface to other devices that might be inside your body, including those nano machines that we have been working on and discussing for now more than 10 years. And I know that to some people sound crazy. Well, believe me, in 11 years, many things have happened. And, well, we're not talking about being that crazy anymore.
The Internet of Things will not only be deployed in the world that can be seen, but at scales that are invisible to the naked eye. This will be with the use of Internet of Nano Things and Internet of Bio-Nano Things. Their use will not only be medical at the cellular level, but industrial, for example in filtration work such as water purification or for dialysis. While there is a lot of research and development going on to overcome the technical and implementation challenges to make this a reality and practical, I asked Dr. Yarnett's opinion on using the nano devices and systems at these high frequencies.
Let's trigger people's minds. And the idea is the following, right? Usually,
but at scales that are invisible to the naked eye. This will be with the use of Internet of Nano Things and Internet of Bio-Nano Things. Their use will not only be medical at the cellular level, but industrial, for example in filtration work such as water purification or for dialysis. Not only be medical at the cellular level, but industrial, for example in filtration work such as water purification or for dialysis. implementation challenges to make this a reality and practical. I asked Dr. Yarnett's opinion on and systems at these high frequencies.
And the idea is the following.
Or for dialysis, or an Internet of bio-nano things, work such as water purification or for dialysis. But industrial, for example, in filtration work such as water purification or for dialysis. While there is a lot of research and development going on to overcome the technical and implementation challenges to make this a reality and practical, I asked Dr. Yarnett's opinion on using the nano devices and systems at these high frequencies.
Let's trigger people's minds. And the idea is the following, right? Usually when we go to high frequencies, people get uneasy because they think that electromagnetic radiation at high frequencies creates interactions with the body, and people tend to think that those are bad. The reality is that, yes, there are interactions of high frequency electromagnetic radiation with the body, but we should not think of those as a problem. In fact, those are the door to new applications. And for example, there is the whole field of nanobiosensing, which is to utilize high frequency electromagnetic radiation at terahertz or even infrared to measure different type of processes going on in your body. And we do have NSF-funded efforts on the detection of specific biomarkers in the blood relating to, in particular, lung cancer. And that's great. There are different groups working on different applications. I know some work going on related to, for example, the detection of skin cancer with terahertz radiation, and all those are possibilities. And that's still not yet everything, because interaction can mean, sensing or measuring the reaction, but can also mean induce a reaction. So we can also talk about controlling. And I know it sounds very scary, but well, if you know what to do with your signals, there is also an opportunity to control some of these biological processes. And again, it sounds scary and it sounds crazy, but well, as long as the National Science Foundation doesn't think it is, we're fine. And we're actually doing some of that work too.
Coming up,
for human lives. Why all that sickness aggravation? And their percentages are increasing. Argonite invented nanoceram, developed in cooperation with NASA, and brings the greatest innovation to the water purification industry. Through thousands of hours and billions of dollars invested in research until nanotechnology was born to lead disruptive changes in our lives. Nanotechnology is to recombine molecules and atoms, creating nanoparticles, then nanomaterials with special exceptional performance. NanoSaver is the best drinking water purifier that filters turbidity, chemicals, especially chlorine, pathogenic microbes, viruses, foul taste and odor. 2 pleated layers of patented filter media with extra bed depth to achieve maximum organics adsorption capacity. The active ingredient filter media, Nano Illumina, ALOOH, fiber, only 2 nanometers in diameter, but highly electropositive. They make nanocarbon tubes, providing a unique combination of high filtration efficiency, capacity, flow rate for particulate adsorption while maintaining a low pressure drop. In addition, powdered activated carbon PAC in pleated filter cartridges also offer best effects for both particulate and chemical adsorption and soluble contaminants such as soluble organics and chlorine. Beside the powder activated carbon, Agion Silver, which being impregnated into zeolite particles with an average particle size of 10 microns, inhibit the growth of bacteria and other organisms on the filters, thereby reducing the probability of leakage of pathogenic microbes downstream. The addition of a carbon block center core provides a greater chlorine adsorption and offers unique particle adsorption technology. Combining with PAC results higher efficiency and capacity for both particulate and chemical adsorption. including soluble contaminants such as soluble trace organics and chlorine. Our precious lives deserve. The high-quality, top-end, luxurious Nano Saver has been designed exclusively to honor the great Nano Ceram. After a series of complicated filtration procedures, water will be extremely pure. And compared with other water purifiers, Nano Saver achieves these without using chemicals or electricity or even wasting 1 gram of your water. With Nano Ceram, Argonide was awarded some famous clients of Nano Ceram. And so on. Our commitments to excellence and Argonide's label are your guarantee. Enjoy the purity. Feel the difference. What is the most sensitive and important element for human lives? Why all that sickness aggravation? And their percentages are increasing. Argonide invented Nano Ceram, developed in cooperation with NASA, and brings the greatest innovation to the water purification industry. Through thousands of hours and billions of dollars invested in research until nanotechnology was born, to lead disruptive changes in our lives. To lead disruptive changes in our lives. To lead disruptive changes in our lives. Industry. Through thousands of hours and billions of dollars invested in research until nanotechnology was born, to lead disruptive changes in our lives.